Ladies and gentlemen, my name is David Brown, and I'm speaking to you about the critical responsibility that structural engineers and designers have to minimize embodied carbon. And the reason for that responsibility is blindingly clear. Construction accounts for a significant part of our greenhouse gas emissions. And within construction, clearly steel and concrete are both important. And therefore, as designers, we have a responsibility towards the planet and towards future generations. I'm sure most people will be aware of the target to limit the rise in global temperatures to 1.5 degrees C. Well, it's already anticipated that that target will be exceeded. So the challenge is not to stay below 1.5 degrees C, but actually to minimize the overshoot. And we do that by decarbonising. So in all aspects of life, we're being asked to decarbonize. In construction, we might think about the embodied carbon and the operational carbon. Over the years, the total has reduced, but the proportion which is allocated to embodied carbon or embodied energy is increasing because we've done things about the operational energy. We've got better levels of insulation. We've got more efficient heating. We're concerned more about air tightness. So therefore, even though the whole life situation has reduced, the proportion which is allocated to embodied energy and embodied carbon becomes a more significant contribution, and that's why it's the target to reduce embodied carbon. So, like very many industries, the steelwork industry has a roadmap to decarbonize. In this case, it's to decarbonize by 2050. Many of these steps are the responsibility of the steel manufacturers. So recently we will have heard about news from British Steel and from Tata about their plans to change their furnaces into electric arc furnaces, which run on scrap. And that has lower embodied carbon. So many designers, of course, are tempted to specify steel from the electric arc furnace route. That has the advantage of making your particular project look good, but it hasn't solved the global problem because the global demand for steel outstrips the volume which can be produced by the electric arc furnace by a factor of 2. So although your project might look good, it's simply shifted the problem to somewhere else in the globe. What we really must do is just use less steel in our case. So there are a number of steps which are allocated to the designer and the specifier, and here they are. And I think there are significant opportunities to reduce embodied carbon by design. And these are not particularly difficult, they're not particularly new, but they can have a very significant impact. And it's those things that I'm going to talk about in the rest of this presentation. So people might recognize this. This is the start of a hierarchy of decisions published by the Institution of Structural Engineers. There are other versions of this. And the first decision, of course, is do we need to construct at all? Can whatever we've got be reused, extended, adapted? And of course, steel is very good for that. If we've decided that we do have to construct something, then there are a number of questions to be answered. And as we go down this triangle, the opportunity to reduce carbon is rather minimized. So the ones towards the top should be our priority. And I think in all of these areas, designers must have a response. It's no longer something that we can just simply pay lip service to. We must be able to address these challenges and explain why we have or why we haven't chosen a solution with minimal embodied carbon. So a number of these issues then, and I'm sure you'll be familiar with many of them. The first one is we shouldn't over-specify the variable action. And the normal variable action that we deal with, particularly in multi-story buildings, would be office loading. And yet very many people will not choose the value which is specified in the UK National Annex of 2.5 kilonewtons a square metre, but they will actually choose 5 plus 1. 5, which represents crowd loading, and 1, which is an allocation for movable partitions. And the reason for that might be that they are allowing for future change of use. But that means that they are allowing for an unpredictable future, an uncertain future, which of course may not happen. And that means that somebody's paying for that allocation in capital cost, but they're also paying for it in an environmental cost. And we need to be sure that we really do need 5 kilonewtons a square metre. Research has shown that over half of designers choose a higher load than the load which is required according to the United Kingdom National Annex. Of course, if you do reduce 5 kilonewtons a square metre to 2.5 kilonewtons per square metre, that has an effect on the eventual design loads. It reduces them by about 30%. So that's really significant. And that will be, of course, throughout the building, and that will find its way into the foundations. When we're thinking about loading it, of course, we should use the reduction factors. So there is one reduction factor for area. There is a second reduction factor, which is really very useful, and that reduces the axial load in lower columns. It's really significant. So if there are more than 10 stories, the reduction factor is 50%. So the axial load in the lower lengths of columns is only half what it would otherwise be. That means we can choose smaller columns, less weight, more lettable floor area, less carbon. That must be an advantage, and we would be derelict if we didn't pay attention to these reduction factors. Second thing about loading is that in the United Kingdom, we have the option of calculating the loads in accordance with expression 610, or the more onerous of 610A and 610B. We should always be using that second option. It's not really any more work at all. Expression 610B is pretty much always the more onerous of the two, so we kind of know it's already going to be that one. You might say, well, it only saves a little bit, maybe about 3%, but then every little saving leads to an overall saving. And this, again, would be throughout the entire structure. When we're thinking about columns, well, it should be the S460 steel is our chosen steel grade for the columns. S460 steel in universal column sections, they're readily available. They have a number of advantages, and it's not just the strength. They are stronger, of course, but there is an advantageous buckling curve. So the improvement in resistance is not just the ratio between S460 and, for example, S355, but there is also a more advantageous buckling curve. So again, lighter weights, smaller columns, more lettable floor area, and less carbon. S460 for universal column sections in multi-story buildings really should be our preferred choice. And then how hard do we work the individual members within the structure? There is some well-known research that says utilizations, that measure of how hard a member is working, they're low and can be very low. And perhaps there are some reasons for that, but I personally believe that those reasons are not very compelling reasons. Even worse, there are some people who limit the utilizations to 80%, and they do that because they say, well, we know between our initial design and the final design that things will change, and therefore they make an allowance for the fact that things will change. The problem with change, they say, is that there simply isn't enough time and there simply isn't enough money to be able to finesse the design. Well, I suggest that the answer to that is that the client must be made aware of their responsibilities towards the planet and towards future generations. And there must be an allocation of time, and there must be an allocation of cost to make sure that we can deliver a design with finesse. We really ought to be working our sections up to 99.9% of their resistance. That doesn't mean that our reliability or levels of safety have been eroded. We already have the partial factors. If we only have a utilization of 0.8, or in many cases even lower, we are simply being overly conservative. So some other reasons to over-design. Well, first of all, to make construction easier, and there is value in that. We don't want to provide, let's say, minimum weight solutions that need expensive reinforcement at the connections. But most of the things that we design don't need that sort of detailing. So minimum weight is a good place to start. Some people say, well, it's done to rationalize members, but most fabrication is done by numerically controlled machinery, and that doesn't care if one member is different to the next member. There is an argument about minimum weights of steel. If we are only specifying a very small number of certain serial sizes, that can turn out to be more expensive, but the steelwork fabricator will be able to advise on those sorts of issues. The key things to me are that there is no penalty for the designer if they over-design. But that might change. It might change as clients become more educated. It might change as targets become embedded in legislation. And then why don't we think about making our members as structurally as efficient as we possibly can and put the resistance where the resistance is needed? That would give us the opportunity to deliver long spans, which have the advantage of being flexible and adaptable, and all those things which are demanded by clients. It doesn't have to mean that we're throwing away lots of material, because in all these different forms of fabricated members, the excess material has value. It's sold as scrap. It's so valuable that even the swarf from drilled holes is recovered and recycled. Then we have methods of design, and most of the time in the United Kingdom we assume that things are simply supported, and we deal with the lateral loads by some system of bracing. We design the beams as pin-ended members, and yet we know in reality it can't be like that. Even nominally pinned connections have some resistance and they have some stiffness. Well, if we use connections carefully, then we can take the benefit of that resistance and the benefit of that stiffness. So we can do semi-continuous design. We can do semi-continuous elastic design. A couple of warnings about that. We just need to be careful because it might involve a bit of iteration, and we need to be confident that we've got the correct connection stiffness. But there are tools which allow us to introduce springs into frame analysis, and there are tools which allow us to calculate the stiffness of connections. So that's all possible. But one very attractive solution is to construct using partial strength semi-rigid connections. People might know those as wind moment connections, but the beauty of those connections are that they have been physically tested. So we know their resistance and we know their stiffness. And that's a really straightforward approach. You'll find it in one of the SCI guides, and all we are doing really is lifting the bending moment diagram, but not lifting it too much, so we're not troubling the column by putting lots of bending moment into the column. That does mean we can choose a smaller member generally, and we might worry therefore about deflection, but not so, because we can use the stiffness of the connections to reduce the deflection. So a really simple, straightforward approach, delivering savings in weight, savings in carbon, And if we are in a brace frame, and many of us generally are in brace frames, a really recommended approach that people should consider. One of our de facto solutions in the United Kingdom is composite construction. And there is a concern that composite construction for some might have become too de facto, too straightforward, and that instead of designing each and every situation, people have a solution which they know works. It worked last time, and therefore they use it again. So they perhaps have a standard slab depth and a standard deck and a certain mesh and a certain concrete, and they don't consider what opportunities there are in the next project that they design. Well, we should. We should be considering double span decking. That will improve the situation. If there are no other constraints such as vibration or acoustics, then probably we ought to choose trapezoidal decking. That has a significant saving and less concrete. We ought to be using propping, and people may say, well, that gets in the way. Well, that might be something that we have to accommodate if we are going to produce a design with the minimal embodied carbon. And instead of starting at 150 mil deep deck, 150 mil deep slab, perhaps we should start at 130 mil and see if we can get that to work. So all these things we can bring together into our de facto solution. And then the floor slab itself, well, instead of the concrete, perhaps we could use fiber reinforcement, or we could use low carbon concrete, or maybe we could do something even more exciting and substitute cross-laminated timber for the floor slab. So relatively new in the UK and perhaps not widely used, but a 140mm slab is quite equivalent to what we would use a composite slab for. They have a really significant benefit in terms of embodied carbon. And we should start to think about using these sorts of solutions. They are of significant benefit to us. And then finally in this section, just a comment about fire resistance and the specification of the protection. To do a good job, one needs to know the utilization of the members, and one needs to know about the ratio of the permanent action to the variable action. And my experience is that that sort of information is not provided to the people who are specifying the coating. And therefore, the only option they have is to make some very conservative assumptions, and that will mean generally an excessive thickness of coating, costing more, taking more time, using more carbon. If we provided the appropriate levels of information, then a more cost-effective and carbon-effective solution could be delivered. These are things that we should do in design, but we should also be thinking about the future, because I'm going to go on to talking about reuse of structures that we built in previous decades. Well, that will surely happen in future decades, and there are things that we should be doing to facilitate that occurring in the future. So one of the problems with reuse is that often we don't know enough about the steelwork. Well, there's no excuse for that. That ought to be embedded with the structure, maybe in the building information model. So perhaps material passports, which tell us that information, perhaps they will be valuable. They certainly ought to be thought about. And we ought to be thinking about, well, how do we make things demountable? What makes it easier to deconstruct our buildings that we build today? And there are methods, even for composite construction, that we should be considering. So yes, designing for today, but also thinking about when we finally come to deconstruct the buildings that we are today designing. So this idea of deconstruction brings us on to reuse. So there are a couple of publications from the SCI. P427 has been around for some time, and P440. And they are both about reuse. The one on the right is a supplement to P427. Why would we be interested in reuse? Well, it's again very straightforward. If we look at the figures on this particular graphic, you'll see that the embodied carbon in reused steel is so much lower than any others. It's unlikely, of course, that we can construct a building entirely out of reused steel. That seems very unlikely indeed, but at least a proportion of most buildings could use reused steel, and that will be beneficial in delivering a building with reduced embodied carbon. One of the barriers would appear to be CE marking of reused steel, but CE marking is an execution issue. CE marking or UKCA marking is covered in 1090. That's an execution standard which talks about how things are done primarily. In fact, it allows the use of other materials from standards which are not cited in the standard. So we're not doing anything which is prohibited, but somehow we seem reluctant to embrace CE marking of reused steel. Our attitude should be that if it's not prohibited, then of course it's allowed. I think this is a temporary problem because there is a CEN technical specification being prepared, and that will of course encourage the CE or UKCA marking of reused steel. If we're going to use any steel, we need to know its properties. So for reused steel, there are a whole range of material properties that we need to know, and the stockist of reused steel is going to determine these properties, some by non-destructive testing and some by destructive testing. So the things that we would expect to find, things like strength, of course, and in some cases we'd be interested in the impact toughness, the Sharpie value, and the carbon equivalent. So those are the things that the steelwork stockist will declare, and from then on the steelwork can be CE marked in the normal way. P427 introduces the concept of a group. This group is going to be tested. So a group is a 20-ton group of the same member from the same building performing the same function with similar detailing. It doesn't have to be precisely identical, but similar building. And we're trying to establish the provenance of this, and then we're trying to establish that the steel group is all of the same group when we determine their material properties. There will be issues with recovered steel, for sure. It's not going to be perfect. So probably, as it's been demolished, it's been cut or sheared. Probably it won't have been treated gently, and therefore there almost certainly will be damage. People get, I think, concerned about damage, but my question will be, well, why do we care? And when do we care about damage? And that really depends on the circumstance. It depends where the damage is. Is it in the high moment zone, or in the high shear zone, or somewhere in between? And what exactly is the damage? Is it damage to a flange or the web? So that does mean that the structural engineer must be involved with making these decisions and reviewing what is proposed. And again, that will take time, and those costs need to be covered by the client. But the goal is a structure with low embodied carbon. Within that 20-ton group, every single piece will be non-destructively hardness tested. From the hardness tests, you can establish the yield strength and the ultimate strength, and from those two values you can decide what steel grade it is. So that's the first way of doing things, to hardness test every single member to make sure that they are of the same group, to establish the strength and therefore the steel grade from those hardness tests, and do one destructive test so that you can demonstrate to yourself that yes, the hardness tests are delivering the correct result. We need, however, to reflect the fact that manufactured steel has a range of properties, and the average strength of steel manufactured today is significantly higher than the minimum. So when we identify the steel grade, we must reflect that. Our target value of minimum strength is significantly higher than the minimum quoted in the product standard. And that's to make sure really that we've got the same statistical distribution as we have with modern produced steel, and therefore our reliability has not been adversely affected. The second opportunity, and this perhaps has more commercial benefits to it because it tends to produce a more realistic view of the steel grade, is to take a number of samples to complete destructive tests on each of those samples and then simply assess the material characteristics by looking at the statistical distribution. And that would all be in accordance with and adhere to the guidance in EN 1990. And if we do that, we'd simply be comparing the value that we calculate with the product standard. What's happening in practice is that determining the steel grade based on hardness alone tends to be conservative. So one might conclude that one has a weaker steel grade than actually it really is. And that's why I say there may be value in doing more destructive tests. It might be important to determine the impact toughness, and for that you would need to do a destructive test, a Sharpie test, particularly if the elements were thick and they were going to be used externally. That might be important. A little plug for one of the other SCI guides. If we're doing that, remember that the Eurocode is based on fatigue, which is a very onerous situation. If fatigue is not a design consideration, then P419 has got some very helpful information, and you will find that there are quite generous limiting thicknesses prescribed in P419. So have a look at that guide if you don't have fatigue in your structure. And of course, most of our multi-story buildings, they don't have fatigue as a design consideration. We might need the carbon equivalent value, so that can be determined from a chemical analysis of the steel. That would be used by the responsible welding coordinator working for the steelwork contractor when they're developing appropriate welding procedures. Some design issues. The cross-sectional resistance, we suggest that there is no need to change anything there. So gamma M naught for the cross-sectional resistance, leave at 1.0. For buckling, we're aware that, well, there may be damage, there may be some tolerance issues, and therefore conservatively, we're going to take gamma M1 as 1.15 multiplied by the national annex value. And to have that product there of 1.15 multiplied by the national annex value is important because, of course, in different countries they may have a different national annex value, and indeed our national annex value may change in 2028 with the second generation Eurocodes. So that's all concerning P427, which was steel used in construction since 1970. But what about steel used pre-1970? Because much of our steel inventory is in buildings which were constructed before 1970. Well, here are some issues because, well, steel certainly had some significant changes in its composition around the time of the Second World War. There were differences in practice, of course. So in the early steel structures, there was certainly no indication of welding whatsoever. They would have been riveted and then later bolted. And it was not for many decades before welding appeared in the design codes. There was not a lot of concern about brittle fracture until after the Liberty ships were lost at the time of the Second World War, and design for very many years, up until 1970, about that sort of period, would have been to an allowable stress code, and that was BS 449. So what do we do about that? Well, we created some non-dimensional buckling curves based on the lookup tables in BS 449. We were interested to find that there were several different curves over the years. A couple of those I'll show you in a moment. And then we created a brand new, slightly conservative curve that you could use with the Eurocode. So here is a slide which shows us how some of the flexural buckling curves changed over the years. Interesting movement. Here is a slide showing how the lateral torsional buckling curves changed over the years. And the dotted purple line is the elastic critical buckling stress. And of course, no resistance should be to the right of that line. So some of those curves from 1959 and 1932 are, in inverted commas, rather interesting. So in P440, we present some very slightly conservative buckling curves compared to those that we find in BS 449. So there is one for flexural buckling, and there is another for lateral torsional buckling. Limited choice with those curves. There is no choice in terms of imperfection factor, for example. They're just the curves which we recommend for use with any steel which was used in construction prior to 1970. Let's imagine then that you need to, or you wish to, reuse steel. You need a stockist, of course, to have steel, and there are several stockists now who have large stocks of readily available steel. You perhaps want to look at your design and use a stock matching tool to have a look at the stock that's available and say, well, yeah, those pieces will be good for me. But then often there is a delay of many months between your initial design and the final fabrication, and steel may well have moved on during that period. So best practice is to set the steelwork contractor a target for reuse. Might be, let's say, 10% of the steel in a new building. The target is that 10% is from reused steel, and allow them to identify the steel at the time that they're going to buy it. And maybe that will mean that the structural engineers need to give effectively envelopes and say, well, members within these size ranges with this sort of second moment of an area, they will be satisfactory for use. And maybe again that will involve reviewing what those proposed sections are, maybe with the damage that that they perhaps have, and making sure that they are okay. So again, maybe there will be additional time, maybe there will be additional input required and additional costs to be covered in making sure that we're producing a minimum embodied carbon solution. So perhaps there are cases where we don't worry about it at all if we can't see the steel. Who cares really what the steel looks like? Who cares whether it's still got cleats or any other fixings on? We don't see it, so that would be okay. But then there will, as I say, I think be additional effort in reviewing those sections which are proposed. So, ladies and gentlemen, that's my presentation finished. Just to say that early in 2024, we should have an update of P427. That was one of the guides I described. And the first half of my presentation, which covered all the opportunities that there are to produce a minimum embodied carbon solution during the design phase. Well, that should be published in spring 2024. But my overall comment is, for structural engineers, it's not just about bending moments and shear force diagrams. It's very much about decarbonising our solution.